Hey everyone, I am Miss Hu, your physics teacher. In this video, we will be going through an overview of Unit 5 Nuclear Physics. This unit is in the IGCSE Physics syllabus for 2023 to 2025. Now, this video is designed to be an overview of this entire unit, so it's not meant for you to learn this topic. So this video is designed more for students who have already learned this entire unit and just need a refresher or a reminder about what is covered in this unit to prepare for their examinations. So if you're learning this unit for the first time, or if you need a particular refresher about selected topics within this unit, please watch my video on those topics instead. So this video is part of a series of revision videos to help students prepare for their upcoming IGCSE examinations. Right, so let's get started. First of all, we need to know about the atom. This is a very basic topic that is covered in chemistry, and even if you don't take chemistry, you should have learned this anyway during Key Stage 3. You need to know the structure of an atom in terms of its positively charged nucleus and that the electrons are in orbit around the nucleus. You also need to know that the term atom automatically means that it's neutral, where there is a balanced number of protons and electrons. Atoms can form charged particles that are known as ions by gaining or losing electrons. So atoms can form positive ions by losing electrons or form negative ions by gaining electrons. You should already know this by now. Now, in addition, you also need to know about the gold foil experiment. So you can see in here, we need to know how the scattering of alpha particles by a sheet of thin metal, which is essentially the gold foil, is able to support the nuclear model of the atom. You need to know about this gold foil experiment and how the results of this experiment provide the hypothesis for the nuclear model. So the nuclear model that we've come up with based on this experiment, for one, states that there's a very small nucleus inside the atom surrounded by mostly empty space. This nucleus contains most of the mass of the atom, and this nucleus is positively charged. So in a nutshell, you need to remember the results of this gold foil experiment and how the results prove all these three. So when we observe the results of the gold foil experiment, we find that most of the alpha particles are able to travel straight through the gold foil, therefore proving that the atom is made up mostly of very empty space. That's why most of the alpha is able to pass through. A small percentage of the alpha particles are scattered, where some will be deflected and they change direction, and a very tiny percentage is reflected backwards. So what these suggest is that there's a very small positively charged core in the center, which causes the positively charged alpha particles to repel, and they change direction as well as reflect. So the name for this positively charged core is the nucleus. So now we go into understanding more about the nucleus. So we need to know what resides inside the nucleus are the protons and neutrons. So the protons are the subatomic particles with a charge of positive. Neutrons have no charge, that means they're neutral, whereas the electrons have a charge of negative. So relative to one another, protons have a charge of positive 1, while electrons have a charge of negative 1. Neutrons, of course, are neutral, no charge. In addition, you also need to know the terms proton number and nuclear number. So let's start first with the term proton number. So the term proton number here refers to the number of protons that are inside the atom. If you can recall what you have learned about the elements in the periodic table, every element has a different proton number. So essentially, the number of protons is what determines what type of element that particular atom is. Or in other words, the type of atom it is. That's why the proton number is also known as the atomic number. The nuclear number, on the other hand, refers to the total number of nucleons. So what's a nucleon? The nucleon refers to whatever's inside the nucleus. So the nucleon number is basically the total number of protons plus the number of neutrons. Now, the mass of a proton and neutron are almost equal. The difference is actually very insignificant. So you want to get the mass of the atom, we can total up the number of protons and neutrons, and that will get us the mass. Why don't we include the electrons? Because the mass of a single electron is so tiny, it has no influence on the total mass. So that's why when it comes to calculating the mass, we will just ignore the number of electrons. For the electrons, you actually need more than 1,800 electrons to make up the mass that matches one proton. So that's why we can just ignore the mass of the electron. So you'll find that because the protons and neutrons have roughly the same mass, the mass of the atom is actually equal to the number of nucleons. So that's why the mass number is the same as the nucleon number. So from this, you should be able to calculate the number of neutrons. Basically, you just take the nucleon number minus the proton number, you can get the number of neutrons. Now you also need to know how to use the nuclide notation of AZX, where A is the nucleon number, Z is the proton number, and A is the element of that particular atom. So if we were to look at the example of these three oxygen atoms below, so the one on the left has 8 protons and 8 neutrons, giving us a total mass number of 16. How we would write this in AZX form? A is the mass number, so that goes on top, 16. Z is the proton number, which is 8, and this is oxygen, so that's how we'll write the nuclide notation for oxygen 16. For oxygen 17, the mass number is 17, so we'll write it as 17 on top. There are 8 protons, and the element is O, so we'll write it as 17, 8, O. For oxygen 18, it would be 18, 8, O. Now, of course, you also need to know what is an isotope and state that an element may have more than one isotope. So by now, you should know that isotopes are atoms of the same element with the same number of protons but different number of neutrons or different number of nucleons. So on this slide, you can see that we have 3 different atoms of the same element, but they have different number of neutrons or different number of nucleons. So oxygen 16, oxygen 17, and oxygen 18 are all isotopes of the same element. All have the same number of protons, but different number of neutrons or different number of nucleons or different masses. Let's move on. Now you also need to know the relationship between the proton number and the relative charge on a nucleus, which is quite basic atomic knowledge, really. So what is the relationship? Basically, if you know that protons are positively charged, the number of protons would influence the relative charge in the nucleus. So for example, if hydrogen has only 1 proton, the relative charge of that nucleus, if we were to ignore the electron on the outside, it has a charge of positive 1. If carbon has 6 protons inside the nucleus has a relative charge of positive 6. Now, if we look at hydrogen, there's no neutrons, so no need to consider neutrons at all. But for carbon, there are 6 neutrons. So why don't we take into consideration the number of neutrons when we calculate the relative charge? That's because neutrons have no charge. So regardless of the number of neutrons, the relative charge is only influenced by the number of protons. So that's why for carbon, 6 protons, 6 neutrons, relative charge, positive 6. For oxygen, 8 protons, 8 neutrons. Neutrons are neutral, so you can ignore that number. 8 protons means that the relative charge of the nucleus is positive 8. Nitrogen, 7 protons, 7 neutrons. Relative charge is positive 7. So please note that I'm referring only to the relative charge of the nucleus. I'm not talking about the overall charge of the atom, including the electrons. Because if you look at what it states here in the syllabus, it's about the relative charge on the nucleus. They didn't mention the electrons that are part of the atom. So nucleus only means the core with the protons and neutrons. Electrons are outside that nucleus. Now, you also need to know the relationship between the nucleon number and the relative mass of the nucleus, which I have already explained just now. So remember, the protons and neutrons have almost equal masses. So when you want to calculate the mass of a nucleus, you just need to total up the number of protons and neutrons, which happen to be equal to the number of nucleons. Therefore, hydrogen has a relative mass of 1. Carbon, relative mass of 12, because 6 protons, 6 neutrons, add them together. Oxygen, 8 protons, 8 neutrons, that gives us 16. And nitrogen, 7 protons, 7 neutrons, 14. Now, let's go on to the detection of radioactivity. So what you need to know is the meaning of background radiation. So background radiation is basically natural radiation that is everywhere. It's radiation that is occurring naturally in the environment. So what that means is that you and I, we're living in an environment right now that has radioactive radiation. So that radiation is known as background radiation. So why aren't we mutating and all that? It's because the level of radiation in background radiation is so low that it actually has no effect on us. Or rather, we've gotten used to that level of background radiation that it has no more effect on us. You do need to know the sources of background radiation, and in your syllabus, you must know these 4 sources. The radon gas in the air comes from the rocks and buildings, food and drink, as well as cosmic rays from the universe. So when I say universe, I mean outer space, from the sky. You also need to know how to detect radioactivity, which in this case we use a detector known as the Geiger counter. Just going to write that here. So this is the Geiger counter, or sometimes known as the Geiger-Müller tube, or GM tube for short. I'm going to just write it here, Geiger counter. So this is an example of one type of Geiger counter. You can see that this tube here, that's the Geiger-Müller tube. This is the tube that you would point towards the radioactive material that we want to measure. And it's connected to a counter, which will give us the value of the level of radioactivity. So that's what they mean here when they say the detector is connected to a counter. Now, when using the Geiger counter to measure the level of radioactivity, this reading is known as the count rate. And the value of this count rate that is shown on the scale is expressed as counts per second or counts per minute. You have to be aware that when using a Geiger counter, obviously it's not only picking up the level of radioactivity from the radioactive material. It also has to include the radioactivity that exists around us, known as background radiation. You cannot eliminate background radiation altogether when we're using the Geiger counter. You can't like, hey, background radiation, go away. I only want to measure the level of radioactivity of the radioactive material. That doesn't work, right? So in order to get the value of the count rate only from the radioactive material, we need to know the value of the background radiation and deduct that from the overall reading. So the term corrected count rate here means the count rate without background radiation. And to get that value, you just take the count rate minus the background radiation. So that's how you get the corrected count rate. Next, let's go into the concept of nuclear emission. So when we talk about radioactivity, it means that the radioactive material is releasing nuclear emission. You have to be aware that the radioactive radiation that's being emitted is from the nucleus, and it's spontaneous and random in direction. In terms of the types of emission, you only learn about alpha, beta, and gamma. So you must know of these 3, as well as their nature, their relative ionizing effects, as well as their relative penetrating abilities. So here's a general table about the 3 types of radiation. You must know that alpha is a helium nucleus, and because helium has 2 protons, its relative charge is positive 2. Among the three, alpha has the highest relative ionizing effects, but the lowest relative penetrating abilities. Alpha is easily stopped by thin paper or human skin. Beta is an electron and therefore it has a charge of negative 1. Compared against the other two, it has medium ionizing effects as well as penetrating abilities. Beta is stopped by a few millimeters of aluminium. Gamma is on the electromagnetic spectrum. It is a high frequency electromagnetic wave. Because it's an electromagnetic wave, it has no charge, so it's neutral. And compared against the other two, it has low ionizing effect but high penetrating abilities. Gamma is not easily stopped. It can be reduced by a few centimeters of lead or a few meters of concrete. So in addition, you also need to know about their deflection, electric fields, and magnetic fields, which I'll explain on the next slide. Let me just quickly explain their relative ionizing effects with reference to their kinetic energy and electric charge. So if you can recall, the formula for kinetic energy is half mv squared. So because alpha has the greatest mass, it has the greatest kinetic energy. Even if the other two are moving fast, but its sheer mass will cause it to have the greatest kinetic energy. For example, like beta has such low mass, in spite of its high speed, it may not have as great kinetic energy as alpha, whereas gamma has no mass, so its kinetic energy is essentially 0. So if we were to compare that understanding of kinetic energy with the ionizing effect, the greater the kinetic energy, the greater its relative ionizing effect. If we were to compare the relative charge against the ionizing effect, you can also see because alpha has 2 protons, in terms of the magnitude of the charge is much higher compared to beta, which is a single electron, and gamma has no charge. So the greater the magnitude of electric charge, the greater the relative ionizing effect. Now let's take a look at the deflection of alpha, beta, and gamma in electric fields and magnetic fields. So what we're looking at here on this diagram are two plates. One is positively charged while the other is negatively charged, which creates an electric field between these two plates. So when we direct the radioactive radiation within this field, we'll find that alpha will be attracted to the negative plate because it's positively charged, whereas beta will be attracted towards the positive plate because it's negatively charged. Gamma has no charge, so there will be no deflection because it's not attracted to either one. That's why it travels in a straight line. In addition to being aware of the opposite deflection directions of alpha and beta, you also need to take note of the angle of deflection. You'll find that beta deflects much quicker at a greater angle compared to alpha, and that's because of its mass. Because electrons have such tiny mass, it's easy for it to change direction. That's why it deflects so much more easily compared to alpha, which has 2 protons to neutrons. Its mass number is 4 compared to the tiny electron, which is like so tiny, 1 out of 1,800 plus. So if we look at the magnetic field, again, you'll see a similar behavior. Alpha and beta would deflect in opposite directions due to their opposite charges, whereas gamma, because there's no charge, will just travel in a straight line. There is no deflection. To determine the direction of deflection for alpha and beta, you need to use Fleming's left-hand rule, where the charge is this time represented by the finger that represents current. So remember, current is from positive to negative. So positive to negative, you take it as alpha moving. Beta is the electron, and just like how electron flow is opposite to current flow, when we want to use this hand to look for beta, because this represents current, right? Or in this case, alpha, positive to negative. Beta electrons are opposite to current, so beta opposite to alpha. So the direction of beta will be opposite to this. So you need to use Fleming's left-hand rule to determine the direction of deflection for alpha and beta. So just going to scribble that here. Now, just to show you some examples of some past year questions so that you are aware of what you need to explain. So this question is taken from paper 4, variant 1 of the winter 2023 paper, where you need to explain why alpha is more strongly ionizing than beta particles. So if you look at the answer scheme, it uses the concept of kinetic energy and charge to explain the reason why alpha is more strongly ionizing than beta. And if you're wondering how are we supposed to know that we're supposed to use the concept of kinetic energy and charge to explain this, that's because it's already given in the syllabus guide. So you need to be able to explain their relative ionizing effects with reference to kinetic energy and electric charge. So that's what they said in the syllabus guide, and that's why that's in the mark scheme. Next, we need to know about radioactive decay. So first of all, you need to know that radioactive decay is because of an unstable nucleus that releases nuclear emissions to become more stable, and these changes are spontaneous and random. So the nuclear emission could be in the form of alpha or beta, or a combination of alpha and gamma or beta and gamma. Now, you also need to know that during alpha or beta decay, the nucleus will change to a different element. And the isotopes that are radioactive are due to too many neutrons, and the nucleus becomes too heavy. That causes it to become unstable, and that's why they release the radioactive emission in order to become more stable. So during the emission of alpha, beta, or gamma, the nucleus is trying to become more stable, and therefore you'll find there's a reduction in the number of the excess neutrons. So in beta, neutron becomes proton and electron. And you need to know how to write the decay equations of alpha, beta, and gamma. So all this, I'm just going to summarize really quickly on the right side over here. So you need to know about the radioactive decay of alpha, beta, and gamma, and you need to know how to write the decay equation for alpha and beta. So let's start with alpha first. So for alpha, let's say we start with the general notation of AZX to represent the alpha source. So if this was a radioisotope that was releasing alpha radiation, we know that alpha is 4 to alpha. What you'll find is that the daughter isotope, that means the atom that was formed after this alpha source has released the alpha radiation, the number of nucleons has reduced by 4. So you'll get a new number of A minus 4. And the proton number would have dropped by 2, so Z minus 2. Now remember, the element is determined by the number of protons. So if the proton number here has changed, the element would also have changed, as mentioned here in number 2. So that's why for the general equation, I'm just going to write here Y to depict another element different from X. Now for beta, you need to be aware that the beta particle, which is the electron, does not come from the orbit around the nucleus. The beta, which is the electron, comes from the nucleus. But the nucleus doesn't have an electron, if you can remember, right? So where does this electron come from? It comes from the splitting of the neutron. So a neutron would split to become a proton and an electron. So this electron is then thrown out of the nucleus while the proton remains in the nucleus. So if we were to write the general decay equation for beta, if AZX were to represent the beta source, this beta source would have thrown out one beta. So we're going to write it this way to show that it's a beta particle and not a random electron. The number of nucleons would remain the same because although the source has lost one neutron, it's gained one proton, so it balances out. But the number of protons would have changed. It would have increased by 1. And a change in the proton number will cause the element to change. So I'm going to write Y in this case to represent a different element from the original X. There is no decay equation for gamma because gamma does not involve any changes in the number of protons or neutrons in the nucleus. It's just an electromagnetic wave. So that's why there is no gamma decay equation. You only need to learn to write the alpha and beta. Now remember that gamma typically accompanies alpha or beta. So if there were any gamma emission, we would just add gamma to the end of the equation. If there was also gamma emission, you just write here plus gamma or plus gamma, like this, if there were. So now let's look at half-life. You need to know the definition of half-life. So the half-life of a particular isotope is the time taken for half the nuclei of that isotope in a sample to decay. And you need to know how to use this in simple calculations. So this could involve information in a table or a decay curve. If you're doing core, you only need to do calculations that do not involve background radiation. Whereas if you were doing extended, then you do need to know how to get the corrected count rate where you need to take away the background radiation. Just be aware that in general, the value of the half-life of a radioisotope is a fixed number. Good news, you don't have to memorize the values of the half-life. The half-life will either be given to you in the exam paper or you have to calculate the half-life. Be aware that in general, a decay curve of any radioisotope looks like this. So it will drop into a curve and the graph will never touch the x-axis. That's because math, right? When something is being halved, half, you will never get zero. You'll get really close, but never zero. Now, this is not written in the syllabus guide, but I'm just adding this in because I've seen this come out in past year questions. So students, you also need to know the benefits of long half-life, or on the flip side, you need to know the dangers of short half-lives. So for example, if we take a look at this question, this was taken from paper 4 variant 1 of the winter 2023 paper. And you can see in this question, you need to explain the advantage of the long half-life for the use and safe disposal of a household smoke alarm. What you need to be aware of is that when a radioactive material has a long half-life, that means that it takes a longer time for the radioactivity to drop to become almost zero. That means throughout that lifespan, it's releasing radioactivity at sparse intervals. So it's not, it's just a little bit here, a little bit here, a little bit here, and slowly dropping down to half. So that's why we consider materials that have very long half-lives to be safer in terms of disposal. So you can see here in the answer, you can see the advantage of the long half-life is because there's a lower initial activity, or you can say few emissions per unit time. And that's why the smoke detectors are not hazardous or they're easy to dispose of. On the flip side, for short half-life, here is a past year question taken from paper 4, variant 1 of the summer 2023 paper, where the half-life of a radioisotope is given as approximately 20 milliseconds. And they want the students to write one reason why isotopes with very short half-lives are especially hazardous. And you can see the answer in the mark scheme here says that it's because there's a large number of particles produced in a short time, there's a high or large decay rate, or a high dose of radiation in a short time. So the understanding behind this is because for the radioactive material to drop to become almost zero, because of the short half-life, it's releasing a lot of radiation in order for it to be able to drop in such a short period of time. So that's why radioactive material with short half-lives are considered to be more dangerous. Now for this slide, I've included a past year question taken from paper 4 variant 2 of the summer 2021 paper, where you need to know how to calculate the half-life from a decay curve where the background radiation has not been subtracted. So never assume that the graph given to you has already been corrected. So this graph shows us a count rate detected. That means the value from the Geiger counter was directly put into the graph and plotted. they've given us a background radiation as 20 counts per minute. So in the subsequent questions where they may ask students to calculate the half-life, you do need to minus the background radiation first. So just to show you very quickly how to calculate the half-life in this kind of case, the initial value that we get over here, we need to minus the background radiation. So if that number is 220, the initial value that we must take is 220 minus 20, giving us 200. So the half-life is the time taken for 200 to drop to become half of that value, which is 100. But you cannot look up the value of 100 from the graph because you must remember the count rate includes the background radiation. So for the number that we look up in the graph, we need to look up the value of 100 plus the background radiation, which is 20. So we need to look up the value of 120. And this is how we get the half-life, which would be, in this case, 2.4 minutes. Next, applications. So you need to be able to explain how the type of radiation emitted and the half-life of an isotope determine which isotope is used for applications. So for your syllabus, you only need to focus on these 5 applications. The household smoke alarm, which uses alpha sources. So why a smoke detector needs to use alpha radiation is because alpha has very high ionizing effects. So the alpha particles help to complete the circuit of a smoke alarm, which has plates placed at a distance from each other, because the ionized air particles can then complete the circuit of the incomplete alarm circuit. So the smoke alarm is able to detect smoke because the smoke particles prevent those ionized air particles from completing the circuit. And when the circuit is incomplete, the alarm would sound. You also need to know that radioactive radiation, specifically gamma radiation, is used to irradiate food to kill bacteria, allowing the food to last for longer because it would reduce the amount of bacteria that exists inside the food that could cause the food to spoil. So the food can last longer, which means it can be exported to other countries and stay on the shelves for a longer period of time. You also need to know that radioactive radiation can be used for the sterilization of equipment, specifically gamma rays. So the kind of equipment that need to be sterilized would be, for example, the utensils that are used in a medical surgery. You also need to be aware that radioactive radiation can help in terms of the measuring and controlling of thicknesses of materials. And the kind of radiation that is used depends on what is being measured. So for example, if we want to use a machine that can automatically control the thickness of a metal sheet, we would use beta because the thickness of the metal can change the amount of beta particles it can pass through. So if it's too thin, more beta can pass through. If it's too thick, less beta can pass through. So the change in the count rate can be linked directly to a machine that can manipulate the amount of pressure that's being applied to the metal to make it automatically thicker or thinner. And also, radioactive radiation can be used in the diagnosis and treatment of cancer, again using gamma rays. So the radioactive isotopes can be placed inside a liquid or in some medicine which the patient drinks, or can be injected into the patient. The medicine that contains those particular radioisotopes with high gamma radiation can be used to target the cancer cells and kill those tumors. Or another way is to use external radioactive radiation, where beams of radiation is then targeted towards the tumor in the patient's body and kill that tumor cell. And finally, we come to safety precautions. So what you need to be able to do in your exams is, for one, you need to state the effects of ionizing nuclear radiations on living things. So this includes cell death, mutation, and cancer. You also need to be able to describe how radioactive materials are moved, used, and stored in a safe way. So remember that the storage needs to be in lead boxes. And why lead? Because lead can reduce or even block low levels of gamma radiation. Alpha and beta can't even pass through lead anyway, so that's why lead is the safest material to use to store and transport the radioactive material. In terms of the safety precautions when handling ionizing radiation, of course, we need to reduce our exposure time, because the less time spent on the radioactive radiation, so the less damage that could happen to the individual. You also need to increase the distance between the radioactive radiation with the living tissue, so greater distance, less radiation, obviously. Or we can use a shield. So that means stand behind something that can block the ionizing radiation from reaching us. And that's it for this unit. So if you found this video to be helpful and educational, please click like and subscribe for more free physics lessons from your physics teacher, Ms. Ho. Happy studying and all the best for your examinations.